Well, a warm welcome. Thank you for joining. Nice to have you here. Get yourself ready with a notebook, a pencil, or a pen. Whatever you choose to write with is fine. This is math from the void. Math coming at you pretty much out of nowhere. And today we have a Calc BC problem from the 2008 AP Calculus BC exam. So if you're an AB, sorry to say this question is not for you. Unless you're familiar with Taylor Polynomials and how they work. You are actually familiar with some type of Taylor polynomial, you just don't realize it yet. So if you're in BC, go ahead and give this question a read. You see they give us this table with a bunch of values, lots of fractions. And we're going to let h be some function with all of these derivatives, all the way up to the fourth derivative. So we're going to use those derivatives to create our Taylor polynomial. Give yourself about 12 minutes. Now, you could use Desmos for the calculator abilities. You won't really need a graphing calculator, but you can use a calculator. I'm going to have a basic pocket calculator at my disposal, so I don't use too much time during the solution. That being said, writing out the polynomials is really going to be what you need to do carefully by hand. And then you can plug in points by using a calculator if you'd like. Okay, let's get started. Part A. Write the first degree Taylor polynomial. Do you guys know what that is? The first degree Taylor polynomial, that's just a tangent line. Yes, so you already know what tangent lines are since Calc 1. It is technically a Taylor polynomial. It's an approximating function that is exact at one point. So how do we write the Taylor polynomial? It's basically going to be f of a, which this is like your y minus y value, but we're adding that y value onto the other side. Oh, I should say f of x, or h of x, really. Getting a little lazy here. H of x is approximately h of 1, because we're centering it, h of 2, because we're centering it at x equals 2, plus h prime at 2 times x minus 2 to the 1 power and over 1 factorial, so I really don't need to write it. Let's go ahead and just plug that in. So this is approximately 80 plus 128 times x minus 2. Now if we want to approximate h of 1.9, we'll simply plug 1.9 in. We'll say again that this is approximately equal to 80 plus 128 times negative 0.1, because 1.9 is smaller. So this is essentially 80 minus 12.8, and that part you can certainly do without a calculator. You're still free to use a calculator if you'd like, but you can probably solve that one without. You should be able to solve that without. Now, is this approximation greater than or less than h of 1.9, like the true value? Well, we're going to say that h of 1.9 is actually greater than this approximation. And the reason why is because h is concave up. So it looks, something like this in some way. So any tangent approximation, whether it's a first degree Taylor polynomial, or even if it's a third degree one, even if it was like kind of curved and touched at a point, it would still sit underneath. So we can say that Taylor polynomials are underestimates here. Okay, yeah, it underestimates that. Now let's get ready to look at part B. Part B is going to have us write the third degree Taylor polynomial. So we just have to use some more terms, and again we're going to use it to approximate h of 1.9. So we're going to get a better approximation, because instead of just using a tangent line that I could just illustrate like that. We're using this like more curved thing, right, which touches at the exact same point as the tangent line, but see how it's like closer to the curve sort of for longer. Do something like that. Okay, let's write that out. So now we're going to say that h of x is approximately h of 2 plus h prime of 2 times x minus 2. So that's the level of precision that we got from the first degree Taylor polynomial. Then we're going to get even more precision because now we're taking into account the concavity. And as we take into account more and more derivatives with a higher degree, 2 factorial is just 2, but I'll leave it as 2 factorial. As we add these terms which have more and more precision, it takes into account any of these, let's call them micro changes, from x equals 2 to x equals 1.9, which is where we're going to approximate. Okay, so we can just go ahead and plug that stuff in. Yeah, we're going to have to write it out first. So this is going to be 80 plus 128x minus 2. Sorry for the sloppy handwriting there. Plus, what is h double prime of 2? I'm basically just reading this entire row here. We're going to have 488 over 3, and then that's over 2. So I guess I can call it 244 over 3 times x minus 2 squared. And then we're going to have, again, 448 over 3 factorial is on the bottom here. So if I want to divide that carefully, I can divide it by 2 and get 244 over 9 x minus 2 cubed. Okay, so this is our approximation. Now let's use it to try to approximate h of 1.9, and it'll be a little bit closer than what we got for the last value. Since it was an underestimate, we're probably going to be adding some stuff to it, right? Since this one was an underestimate, if we're going to get closer, then we're going to have to get more than 67.2. So that's a good thing to be able to check with your work. Go ahead and plug that into Desmos if you'd like. Let's see. We're going to have 244 over 9 times 0.1, 0.1, 0.1. So this is negative 0.027 ones forever. Times 0.1 times 0.1. This is going to be plus 0.813 forever. That's actually 3 times this other one. And then here we're going to have, well, those two we already know that they come up to be 67.2. So let's say plus 67.2 minus 0.0271111. And we should get 67.986. Okay, so that's a better approximation for h of 1.9. And we don't have to really justify anything there. I kind of wrote that as if it was coming from the error bound. This is coming from part B. Now let's look at part C. Use the Lagrange error bound to show that the third degree Taylor polynomial is within, or in other words, has error less than 3 times 10 to the minus 4, which, just to let you know, is 0.0003. So we want to show that that is the maximum error that we have. And the way we do that, if we kind of build off of what we did from A to B, B gave us these extra terms, right? And these extra terms added a little bit of precision. But the amount that we're adding each time, it's decreasing because we need a smaller and smaller correction as we go. Now what we're going to do is we're going to show that if we had the next term that we would be adding, it definitely would not exceed this much that we would be adding, which shows us that we were within that much of the true value. So let's take a look at that. Let's take a look at what the fourth term would be. We would say, like, in the Taylor polynomial, we would be using, not f, the fourth derivative at 2 over 4 factorial times x minus 2 to the fourth. That would be the term. And the reason why this is valid is because on the interval from 1.9 to 2, the derivative is maximal. So we'll say the max for the fourth derivative is at x equals 2. So we're going to take the most possible change, like the most possible deviation that we could be, as much change as possible. We're going to take that into account, and we'll still want to show that it's within 0.003. Okay, so how do we do that? Well, we have to take h4, the fourth derivative of h, at 2, that's 584 over 9. So this would be 584 over 9 over 4 factorial, and then times x minus 2 to the fourth. That's going to be the fourth term. So if we're trying to plug in x equals 1.9, that means we're going to have 584 over, what is this? I'm just going to put 3 cubed times 2 cubed. That's pretty much what that is. And let's go ahead and plug in 1.9. Let's see, can we divide this by 2? Yeah, we can divide this by 2, and that gives us 292. And then we can cancel another power of that, and that leaves us with 146. And then we can cancel another factor of 2, and that leaves us with 73. Now, I'm not saying you should do any of this by hand necessarily, but 73 over 27 times negative 0.1 to the fourth. That negative 0.1 to the fourth is going to take it way low. So let's see, 73 over 27, and then times 0.1, times 0.1, times 0.1, times 0.1. Now, if you did 73 over 27, you should have something promising, because that's something like 2.7037. That's less than 3. And then if we're multiplying this by 0.00001, that's sort of helpful there, right? Because that's going to give us 0.00027, which is definitely less than 3 times 10 to the minus 4. So we are within the error that we need to be. Now, if we plugged in a different x value, if we were further away, we might have a larger amount of error. It would not be within that. But since we're close enough to the 2, all kind of worked out. All right, so this problem gave you a chart with a bunch of values, some of which you didn't need. We didn't really need these at all. I guess they just wanted to have a very full chart with several layers of derivatives, so that tells you that you're going to go up to at least like the third degree Taylor polynomial, possibly the fourth one. We used that fourth term for the error bound. But other than that, we're just writing this out. I love that they included first degree Taylor polynomial instead of calling it a tangent line. That really is what it is. All right, I think that's enough blab out of me. Oh, right, talking about underestimates and overestimates, might as well mention that. Whenever you have a concave up function, you can sort of see this diagram. Black is the actual function. Purple is the first degree Taylor polynomial, aka the tangent line, and it will always be underneath a concave up function. So will any Taylor polynomial that's approximating. But as we have a more precise, higher degree Taylor polynomial, it will be closer to the curve. It'll sort of hug it closer for longer. So go up to your loved ones and be like a really high degree Taylor polynomial. Give them a nice close big hug. Anyway, that's enough blab. For reals this time, out of me. I'll see you guys next time in the void.